Oh, okay, 7.2 dot product. So far in Unit 7, we've learned that we can express any vector as a Cartesian vector. So let's say we had vector b. We can express it as a Cartesian vector, and we can resolve it into its horizontal and vertical components. Okay, so we could call this b sub x for the horizontal component of b, and b sub y for the vertical component of b. And we could write the vector b, we could express it as the vector bx comma by, where bx is the horizontal component and by is the vertical component of vector b. Now, what if there are two forces acting on an object? What if we're dealing with two vectors? Well, we could take vector b, which we already have talked about here, and we're going to add vector a. They're both going to be acting on an object. Well, what we would need to do there is simply to figure out what the force that they're applying together. We could take the x component of b and add it to the x component of a, and then we could take the y component of b and add it to the y component of a. So what we would be looking at then is this. We'd have vector a plus vector b is equal to the x component of a plus the x component of b and the y component of a plus the y component of b. And that would give us the resultant vector, right? That would give us the resultant vector a plus b. And that would look something like this, where we could, finish our parallelogram components here. And then we would have the resultant vector a plus b. Now we also know the effect of multiplying either one of these vectors or both of these vectors by a scalar, right? If we doubled vector A and wrote 2A, and then we doubled the length of it, the magnitude, we wouldn't change the direction by multiplying by a scalar, we simply change the magnitude, and that would make the resultant come somewhere over here and much longer, because this would then be like that, and this would be like that. We know how to do that. We would end up just multiplying the x and y components of A by 2. So we would end up with a 2 here and a 2 here, and then we'd add them together. And that would give our resultant vector. So we know how to do that. Multiply vectors by a scalar. We know how to add and subtract vectors. We know how to resolve them into their horizontal and vertical components. Today, we're learning about dot product. It's brand new to you. It is a special operation that is only used when we're working with vectors. In later lessons, we're going to learn a whole bunch of different applications of it. They're used extensively in animation and in video games, and also in calculating. Today, what we're going to talk about is figuring out the mechanical work being done, or simply the work being performed to accomplish a task or to move an object. Okay, so we have an object and you have two forces working on that object. You could calculate the amount of work that is being done with regard to the displacement of that object. And we're going to talk about that in more detail. So it's going to give the work being performed in a particular direction. Basically, it's multiplication with vectors. But we know that vectors aren't just a value. They are a measurement. They're a quantity that has magnitude and direction. Okay? So let's talk about this. Basically, the multiplication of two vectors, if we had a vector here and we had a vector here, okay, we could calculate the amount of work that is being done if this is our displacement vector. So we have a displacement vector S, and that is in the direction of motion. And then let's say you are pulling an object, okay? But you're holding it here, you're actually pulling up, okay? You're actually pulling up on the object slightly and forward. So what we would need to do then is talk about the amount of work that you're doing in the direction of motion. Okay, now if you're pulling, just on a side, if you're pulling the exact same direction as motion, that's really easy to calculate, okay? But as soon as you're pulling, not all of your effort or energy is going into the direction of motion, then all of a sudden you have a difference between the direction of motion and the direction that the force is heading. That difference is represented by the angle theta. Now, if this is your force being acted on the object, then what is the calculation of the amount of work that you are doing on the object in the direction of motion? Well, let's go back and think about some trigonometry. If we're in our unit circle, and you have the direction of motion, but your force is pulling this direction, what you really need is to calculate the amount of work done in the direction of motion. Well, if this is theta, then that's simply if this is F, it's simply the x component, the horizontal component of the force vector F, which is cosine of theta. And now if we take this out of the unit circle and we extend our vector as I have done already, then what you're really looking at is taking the cosine of theta and multiplying it by the magnitude, multiplying it essentially by the amount of force that you're putting in at that angle. Okay, hopefully that makes a bit of sense, and we're going to talk about it as we move along as well. So what happens then if you're working in the same direction? Maybe I'll draw a few more diagrams down here. So let's say here's my direction of motion, and I'm going to do maybe 3 diagrams to kind of get us thinking about it. If I'm working in the same direction as my direction of motion, it's pretty easy to calculate. It's just going to be the magnitude of my force times the magnitude of the direction of the displacement vector, okay? But what if I have motion, I'm intending to have motion going this way, but I'm pulling straight up? Is any work going to be done in this direction? No, it's going to be zero work being done, okay? Now what if I want a direction of motion this way, and I am actually going to pull at an angle of 180 degrees. That's where I'm going to apply my force. Well, now we're going to have negative work being done. Is this starting to make sense? What if I head straight down? If I'm pulling down on the object when I'm trying to move it to the right, 0 work is going to be done, okay? Now, let's look at this one for a second. One more quick diagram. Let's say that the displacement is only going to be 1 unit. So the magnitude of my displacement is only 1 unit, okay? And I'm applying force exactly in that direction. Well, now it's really easy to see because the cosine of theta, when theta is 0, so the cosine of 0 is 1. It's the x distance on the unit circle. The cosine of 0 is 1 because this is 1, 0. So we're talking about horizontal displacement. So it's really easy to see here that if displacement magnitude is 1, then the force being acted on it in the same direction is 1. Okay? Now let's make our force vector. I'm talking about vectors with a magnitude of 1 right now just to help us get that concept. Then the dot product in this case is 1. If the force vector has a magnitude of 1 and the displacement has a magnitude of 1, then the dot product is just s times f, which is 1. As soon as we start to move this thing up and around, okay, you're getting into your exact values on a unit circle, but we're still considering this has a magnitude of 1, right? Let me just say that. Magnitude of 1. Okay? Now all of a sudden, we have only the x component of the force times its magnitude, and since its magnitude is 1, because we're going to just think in terms of a unit circle right now, then all we have is the cosine of the angle theta. That's our answer, because it's a cosine of the angle theta times the magnitude of your force vector. It's going to get you this. And since we're only moving it 1 unit, okay, we're going to multiply that by a displacement vector with magnitude 1. Anything times 1 is itself. Okay, time to get into something else. Now, what if we're on a hill, and the direction of the hill kind of looks like that, and you're holding a sled, so your hand is actually off of, you've got a sled attached, here's our sled, attached to a rope, and you're pulling it. You're pulling in that direction, okay? It does not matter. This is like a cross-section of that hill, okay? I've cut it, and that's the hill, and that's where you're pulling. The only thing that we're interested in is the relative difference between the angle of the hill and the angle being pulled. So we're not actually interested in this angle at all. If this is S with its magnitude and direction, and this is F with its magnitude and its direction, then the calculation of work being done is going to be based on the component vector of F right here that is in the same direction as the displacement vector S. Okay, so again, this forms a right angle triangle, and we can call this, I could turn this picture and I could say, oh, okay, look, I can make it flat and say, okay, now we can clearly see this is our horizontal component. But it doesn't matter which direction S is going. We're always going to talk about vector F with respect to the direction of vector S. And so this right here, this red arrow that I've drawn here, is still going, we're not going to call it the horizontal component of F, but it is the X component of F. Okay, that's just an easy way to talk about it. And it is defined by the magnitude of F times the cosine of theta, whatever theta is. Okay, and then we're going to take that component and we're going to multiply it by the displacement vector S. This right here is the definition of the dot product S dot F. Okay? That's a basic breakdown, basic introduction to what dot product is, how it can be used, etc. We're going to get into our examples now. In example 1, we're going to find the work performed. Find the work performed. We've got Max. Max is pulling his sled up a hill, and Max has a force. Max has a force of 120 newtons at an angle of 20 degrees to the surface of the hill, to the hill. The hill is 100 meters long. Hill is 100 meters long. Find the work that Max performs in bringing his sled to the top of the hill. So, work performed. Question mark. Basic drawing. Okay, I'm going to give you a cross section of the hill. Let's say the hill looks something like that. And then we have our buddy Max. Max is pulling on his sled at an angle of 20 degrees to the hill. 20 degrees. and he's acting with a force of 120 newtons. Okay, now this 20 degrees gives us the angle, the difference in direction between the hill itself and the direction that Max is pulling. And what it allows us to do is draw a right angle triangle where the upward direction here as our component of Max's vector is perpendicular to the slope of the hill. Okay, so again, this is an important point. If we have a vector that is a force acting on an object and the object is heading in a particular direction, then the component vectors of that force vector are the vector going in the same direction as the displacement vector and the vector perpendicular to the direction vector. Okay, so what do we have? We have two component vectors. This is kind of notes again as well as an example, but that's okay. This is a component vector of the force vector that Max is pulling on the sled. This is a component of F in the direction of S, okay? Where this guy right here is the displacement vector S. So this is component of F in direction of S, and this guy right here, right, this is the component of F perpendicular to S. Okay, those are the components that we're going to be talking about every single time. And it is fair to call this F sub X and this F sub Y. They can really be called whatever they want, but what we already actually know about this length right here is that it is going to be the magnitude of F times the cosine of theta. All right? And we know in this case, we know the magnitude of F is 120, and we know that theta is 20 degrees. All right? And so let's go from this triangle. We already know what this component is going to be. Okay? So let's solve this length first. The direction component, the component of vector F in the direction of displacement, is going to be the magnitude of F times the cosine of theta, and that is 120 times the cosine of 20 degrees, which is I'm going to put this in my calculator for a second. 120 cosine of 20 degrees is 112, approximately 112.76. But we're not interested in the magnitude of this component. We're interested in the work being done, okay? Now, a little bit of a note for the work being done. Mechanical work or mechanical work, sorry for mixing in some notes into this example, but mechanical work or just work is the product of the magnitude of the displacement traveled, the product of the magnitude of the displacement traveled the product of the magnitude of the displacement traveled and the magnitude of the force applied in the direction of motion. And the magnitude of the force applied in the direction of motion. All right, so that is the magnitude of the displacement traveled times the magnitude of the force applied in the direction of motion, which is the magnitude of F times the cosine of theta. All right, so this is the formula for the amount of work being done. Now we've done one part of that. I didn't need to necessarily figure it out and get this value, okay? Probably just erase that, because now we want to talk about the work being done. Well, the work being done is the displacement, the magnitude of the displacement vector times the length of this component vector. Just going to write the formula again. Okay, plug in what we have. The magnitude of the direction vector is 100 because we know that the hill is 100 meters long. The force being applied is 120 newtons. And the direction with respect to the direction of motion is 20 degrees. And we put this in, we get approximately 11,276. And because we're talking about work, this is measured in energy. So this is measured in joules. So for Max to get his sled to the top of the hill, 100-meter hill, he needs to exert 11,276 joules of energy, or we could say the work done by Max. The work done by Max is 11,276 joules. So again, the work done by Max, or in any situation, what we figured out is called the dot product. The dot product. And the dot product basically says that for any two vectors, A and B, the dot product of A dot B is equal to the magnitude of A times the magnitude of B cos theta, where theta is the difference between the two angles. Sorry, is the angle in between the two vectors. So the first vector indicates the direction of motion, and then this part is the component vector of B that's in the same direction as motion. Okay, so this part right here then is the magnitude of B times the cosine of theta, and all we're doing then is taking this vector and multiplying it by this vector. That is called the dot product. Okay, we're always going to arrange these vectors tail to tail, and they're going to be somewhere between 0 and 180 for our purposes. And the result of this, the answer, is not going to be a vector. It's going to be a calculation of the amount of work being done. So the dot product is not a scalar. It is a scalar. It's not a vector. The dot product, let's just say it like this. The dot product of two vectors is a scalar quantity, and the units are going to depend on the application that we're doing. So in the first one, in the example that we did, we had units of joules because we were measuring energy or work being done. But there are other applications of the dot product. So the unit is going to depend, scalar quantity, the unit of measure will depend on the application. And again, this diagram I drew with A being the horizontal, but A can be any at any direction. Okay. And then this component of B is going to be the same direction as the first vector, as vector A, and this component of B is going to be perpendicular to vector A. Okay, so here I have the exact same diagram, where here we have the magnitude of B times the cosine of angle theta, because that's the component of B that's heading in the same direction as the initial vector, the first vector A. And then we're going to just multiply those guys together to get the dot product. So example 2. We're going to do some dot products, right? Dot products. We're given diagrams. There's 3 of them that we're going to be doing. And we're just going to use the formula that we've got to calculate them. So A, again, I'm just kind of doing a best effort here. So I have vector A right here. I'm told that its magnitude is 20 degrees. Sorry, not 20 degrees, it's 20. No units given. And we have vector B. We're told that its magnitude is 30. Now, I don't care if for basic problems, I don't care what direction these guys are heading in. I only need to know the relationship between them. So they're separated by an angle of 40 degrees. All right. So let's go ahead and finish this one. The dot product, A dot B, is equal to the magnitude of our initial vector A, so that's the first one here, times the B times the component of B that's going in the same direction as A. So we're looking at the magnitude of B times the cosine of angle theta. Okay, let's plug in what we know. We know the magnitude of A is 20, magnitude of B is 30, and the angle between them is 40 degrees. Type that in your calculator carefully. Double check. You should get 459.6. No units are given as far as what we're working with here, the application. So that's a final answer. Okay, scalar quantity. I'm going to draw B. All right, in B, we have 2 vectors that are perpendicular to each other. All right, so if you're thinking about this as a direction of motion, we've already talked about it, right? And you're pulling down, I suppose. What are you going to end up, how much work are you going to end up doing in the direction of vector M? Well, it doesn't matter what these quantities are, what these magnitudes are, but we're told that the magnitude of vector M is 60, the magnitude of vector N is 75, and we need to calculate their dot product. M dot N is equal to the magnitude of M times the magnitude of N times the cosine of angle theta. Well, angle theta is 90 degrees. What's the cosine of 90 degrees? Right. The cosine of 90 degrees is 0. So this whole thing is going to be 0. But I'll sub in what we know just because. We've got 60 times 75 times 0. Or maybe I'll just write the cosine of 90 degrees. That's the angle in between them. And it's going to be 0. Good. in C, we have, again, another diagram. We have two vectors. We have the vector u, and we're told that the magnitude of u is 100. And then we have vector v. We're told that the vector v is a magnitude of 85. That's a bit long in my diagram, but there you go. And then we're told that the angle in between them is 120 degrees. Now, let's talk about this. Vector u is here in this direction. And basically, if we had a vector heading anywhere in this direction or in this direction, we'd get a positive value for the work being done in this direction. If we went straight up perpendicular to vector u, okay, then we'd be looking at 0 work being done. But now we're actually pulling beyond 90 degrees. We're pulling mostly in the opposite direction of vector u. So the work being done in this direction is actually going to be negative. Let's see how that plays out. We've got u dot v. That's going to be equal to the magnitude of u times the magnitude of v times the cosine of the angle in between them. We're told that u is 100, magnitude of 100. V has a magnitude of 85. And the angle in between them is 120 degrees. Go ahead and carefully type that into your calculator. You end up with negative 4,250. All right, so again, it doesn't matter what direction these two vectors are going in. We care about the angle in between them. You can kind of see how you could do a proof for this with regard to cosine law. At any rate, it's not where we're at or what we're doing, but it's related to that, certainly. And then what else was I going to say? So we have the direction of the vectors with relation to each other, so the angle in between them. And they just gave us right away the magnitude of each vector. Okay, you can assume that later on as you're working in more difficult problems that you're going to have to actually determine the magnitude of a particular vector and then use that information in your dot product calculation. For example 3, we're working with some of the basically algebraic properties of dot product. So properties of the dot product. And again, the properties are the same as always. You have the commutative property, which says you can kind of move things around if like u dot v is equal to v dot u. Okay, that is commutative property. Then you have the associative property. The associative property allows you to say that if you have a scalar quantity times the vector u, and then you have that quantity dot v, because it's basically multiplication in between each of these, what you can do is you can take that scalar multiplier out and you can do the dot product of your two vectors, right, which is essentially multiplication with vectors. And if it's helpful, you can even rearrange this to multiply k times your vector v first and take u dot kv. Okay, so whichever way you want to do this, these are all the exact same. That is the associative property. Distributive property works as well. Okay, so if you have the sum of vector v and vector w, and then they're going to be dot product with vector u. Okay, this is the same as doing distributing u dot v plus u dot w. Okay, what is this? This is distributive product. Distributive property, not product. distributive property. The only other one that you are going to want to know is the if and only if, that term, and perpendicular vectors. So I'm going to just write it. So we got 1, 2, 3, fourth thing to think about. If, sorry, let's do it this way. And I'm just going to use symbols. U is perpendicular to V if and only if, and I'll explain that statement in a second. U is perpendicular to V if and only if U dot V equals 0. Okay? The statement if and only if means it works both ways. If U and V are perpendicular, U dot V must be 0. If U dot V is 0, U must be perpendicular to V. Okay? That statement simply means that it goes both ways equivocally. Yeah? It's not always the case in math or in anything. But in this, if you use if and only if, it means yes. If you get that it's the dot product is 0, then you know they're perpendicular. If you get that they're perpendicular, then you know that the dot product is 0. Okay? And basically in example 3, we're just going to be applying those properties. So using the properties in A, we're told that we're going to have k times the vector u dot, and brackets, u plus v. All right, well, what we can do here is use our distributive property first. Distributive property is basically going to say, okay, take that, dot that, and that, dot that. So what do we end up with? We end up with ku dot u plus ku dot v. And now we can use the associative property to not group these guys together, but to group our u's together. So we're going to go k times u dot u. And here we're going to go k times u dot v. Okay, make a little note of what we're doing here. This first one was distributive. This is associative. And then we're going to simplify. So this is u dot u. We can actually write that as u squared. And we know the final answer is going to be a scalar quantity. So in a dot product, the final answer is a scalar quantity. So we're just taking the magnitude of u, simplifying this, the magnitude of u squared. And over here, because we don't know exactly what u and v are or how they relate to each other, we know these guys are going the same direction. Okay, so this force is being applied in the same direction, u and u. But over here we don't know, so I have to leave it as u dot v. I guess we could have put this as a property, this thing that I just did. That should probably be a property in our list somewhere. So I don't know if you have room underneath. I'm going to pretend like I have room right here. And I'm just going to say that u dot u equals, right, the magnitude of u squared. Again, that's because you can totally disregard the angle in between them. So what you would be ending up with is, if you had, you know, normally it would look like this, right? But the angle between them is 0. Cosine of 0 is 1. So you would just end up with the magnitude of u times the magnitude of u, which is the magnitude of u squared. All right, B, 3b. 3b gives us r plus s dot r minus s. All right, this shouldn't be that hard. I'm actually not going to do this one. I see a plus b times a minus b. This is the product of a sum and a difference, and it's going to end up being the difference of squares. So what you end up with then is, I'll do it in 2 steps. You end up with r dot r minus s dot s, okay? And just like up here, right here, anything dot itself is just its magnitude squared. So what we end up with here is the magnitude of r squared minus the magnitude of s squared, which is really just an application of the product of a sum and difference is equal to the difference of squares. Okay, you could work this out using distributive property, associative property, and commutative property, and you would just end up with this. Yeah, or you could kind of, yeah, you could FOIL this basically. This RR, and then you'd have negative RS, and then you'd have positive RS, which would cancel out, and then you'd have negative S squared. So it's right there. On page 373 in your textbook, we have the proof or the explanation for applying dot product to Cartesian vectors. I'm not going to do that whole proof. I'm just going to tell you what it ends up being. The dot product for Cartesian vectors. So basically now, different from our other examples, we're going to be told the specific direction of both of the vectors involved rather than just relating them to each other like geometric vectors, okay, where we're just looking at the angle in between them. Now we're looking at Cartesian vectors where you have a specific direction and a specific direction, okay? Again, it's an application of the cosine law, and so if we have vector A, which is defined by the coordinates a1, a2, and vector B, defined by the coordinates b1, b2, then A dot B is equal to a1, b1 plus a2, b2. And again, if you'd like a more full explanation of this, you can head to page 300, page 373 to see how that proof works through a triangle ABC and the cosine law. We are just going to go ahead and apply it in example 4, dot product for Cartesian vectors. And in A, we are told that the vector u is 5, negative 3, and the vector v is 4, 7, and we're asked to get the dot product. So u dot v is equal to, according to our definition up here, we just need the first value. So we typically take the first value, u1, which is 5. We're going to multiply that by v1, which is 4. And then we're going to add, take the first value, the value of u, the second value of u, sorry, negative 3, multiply that by the second value of v, which is 7. Simplify this is 20 minus 21. Final answer of negative 1. And we remember this is the work being done. It's not a vector quantity, it's a scalar quantity. And here we don't have the units defined, but that's okay. B, we are told that u is the vector defined by negative 2, 9. Sorry, square bracket. And v is the vector negative 1, 0. And so we're going to take the dot product, u dot v. And again, we're going to take the first value times the first value. That's going to be negative 2 times negative 1. We're going to add 9 times 0. It's going to get us positive 2 plus 0, just positive 2. Example 5. Example 5. asks us to use our amazing vector dot product skills and prove a dot product property. And we're going to do it two different ways. One of them is going to be a legitimate proof, and one of them is just going to be an example to verify. So this is verify property with an example. And then after we do that, we're going to go over here and do B. We're going to actually prove it algebraically. Prove algebraically. Okay, so what are we doing? We are supposed to prove that, here's the property that we're going to prove. We're going to prove that A dot A actually does equal the magnitude of A squared. And we want to prove that for all vectors, any vector A, okay? So we're just going to pick any vector A. Let A be the vector 2, 5. Okay, so this isn't a proof. We're just verifying that this actually works out in this randomly chosen case. So left side is A dot A, A dot A. Right side is the magnitude of A squared. So let's perform the dot product as we would typically with vector 2, 5 and vector 2, 5. Okay, so we've got 2, 5 dot 2, 5. What do we do here? According to Cartesian vector dot product properties, we're just going to take the first times the first plus second times the second. We end up with 4 plus 25 equals 29. Let's look at the right side. The magnitude of A squared. Okay, well that's the magnitude of vector 2, 5 squared. The magnitude of this vector, if we have a horizontal component and a y component and a right angle triangle, an x component and a y component, or just perpendicular components. Again, it doesn't have to be a horizontal and a vertical, but at any rate, we have got then the square root of 2 squared plus 5 squared, and we're going to square that. That's Pythagorean theorem here, and then we're squaring it. And we end up with, in the brackets, we've got the square root of 29, and we're squaring it. Well, the square root of its square, or the square of a square root, is just the value inside there is 29. So left side equals right side. We've verified that this property rings true for this particular case. That doesn't prove anything, but it does verify it with a specific example. Now, to prove it algebraically, we're going to follow the same steps. But this time we're not going to sub in 2, 5 because we don't know what this particular vector is. So we're going to let A be a different vector this time. We're going to let A be simply the vector A1, A2. Okay? And then on the left side we have A dot A. On the right side, sorry for cramming it in here. For the right side we have the magnitude of A squared. So working down this left side then, if we've defined A as A1, A2, then I'm just going to plug that in there. A1, comma, A2 dot A1, comma, A2. In order to take the dot product of Cartesian vectors, we're going to take the first value of the first vector and multiply it by the first value of the second vector. And we're going to add that to the second value of the first vector times the second value of the second vector, which gives us A1 squared plus A2 squared. Over here, the vector A is A1, A2. We're squaring that. which means inside our bracket here, we're taking the square root of a1 squared plus a2 squared, and we're squaring that. And if you square a square root, you just get what's inside, which is a1 squared plus a2 squared. Da-da-da, left side equals right side, okay? An algebraic proof for this property up here to show that it's true for any vector at all, okay? Your practice problems for lesson 7.2 are found on page 375. You're responsible to know how to do numbers 1 through 18. Thanks for watching.